King of the Hill. Been watching a
Yeah.
lot.
Yeah, that's great. Did you ever see the one where Bobby got a job working at the
Yeah.
racetrack?
I know what that feels like to have a boss like that before. I think we all do.
Dad, I think my boss might be a moron. Look here, son. You don't need to trash talk your boss just because he makes you do things you don't want to. Oh, that was great. You owe me 8. All right, we should probably get started on physics. It looks like most of you guys are here. I got 17 folks in the classroom, so we're ready to roll. We're starting chapter 4 today, which is called Newton's Laws of Motion, Dynamics, or actually it's called Dynamics, Newton's Laws of Motion. And really physics is broken up into mechanics and fluid mechanics, which is somewhat related, but wasn't really done that much by Newton. That's done much later by various people, including Bernoulli and Pascal and Blaise Pascal, that is, and stuff like that. Mechanics in general, not necessarily talking about fluid dynamics or fluid mechanics, was more or less created by Galileo and Newton. Galileo handled the kinematic side mostly, and some of the dynamics as well. But specifically, remember, kinematics is the study of motion. Like if I tell you what an object's velocity initially is and what its acceleration, maybe even as a function of time, is, you can determine where it will be, what its speed will be at any time thereafter. That's kinematics, because you're ignoring whatever caused that motion, whatever caused that initial velocity or that initial acceleration. The dynamics portion, which we're dealing with today, is all about, well, what did cause that initial velocity and what did cause that acceleration? And this was mostly done by Newton. And I'm going to talk a little bit about the history of Newton, because most people don't get to read any of the history of Newton. And there's recently came out, I say recently, it's probably been 10 years ago, James Gleick, who wrote Genius and also wrote the book Chaos, is a good science writer. But the book Genius is about Richard Feynman. The book Chaos is about chaos, as well as some of the people that created the ideas of chaos, like one guy studying the 25-hour day or something like that. It might have been the 23-hour, I can't remember. I think it was 24 though. And how basically things change, and basically a strong dependence on initial conditions can lead to extremely hugely different results, even with very small differences in the initial conditions. That's sort of the hallmark of chaos theory. But this guy wrote that book on that, a layman's book on chaos, and of course a biography of Feynman. And now he wrote, like about 10 years ago, a little thin book about that thick on Newton's life, and it's just called Newton. And it's a really good little biography. So I'd like to share a little bit of that with you. So Newton once said, "If I have seen further than others, it's only because I stood on the shoulders of giants." And that sounds like a really humble thing. And those of you who know anything about Newton knows that, yeah, he's probably not very humble. And nor should he necessarily be, because he was a brilliant person. He did more for science than anybody before him, and just as much as just about anybody since him. So he's really, really that brilliant. And he's a recluse. He had a rough life. He was born of a mother who was unwed. The man that impregnated her left her before Newton was born, and it's my understanding that they were unwed. I might be wrong on that, but anyways, the guy was a jerk and left them, abandoned them. She had an apple orchard, and she had like a brother-in-law or uncle or something that would come and check on her from time to time and stuff like that. She may have been a sex worker to make ends meet. There's some history behind that, some documentation suggesting that might be, but that could have been just insults from neighbors. They don't like women living by themselves in that era. But Newton grew up without a dad, but he did have this church figure that was like an uncle to him or whatever. And he noticed that Newton was, curious, good kid, worked hard, liked to learn. And in fact, he started bringing him books from the library at Cambridge and the library from his church. And he wasn't a wealthy guy, but he made decent money and could afford things that a lot of people couldn't, especially the mother. And he would bring Newton, for instance, books on mathematics. And he was like, Newton would really like get excited about those books and want more, like immediately. Like he'd see him one day, and then 2 weeks later, he's finished all five books. And he's like, well, what do you mean? What are you doing with these books? He said, well, I'm working them out. And he's like, what do you mean by working them out? And he pulled out this, ream of papers where Newton was basically proving everything that the mathematics books were saying. So he realized that Newton was pretty bright at math, and he kept bringing him books. And then finally he went to the mother and said, I think Newton, Isaac needs to go to Cambridge. And she said, oh no, I can't afford that. I think he was 13 or 14 at the time. And he said, no. He said, I don't make a lot of money, but I make some money, and I can afford to send him if you just let me. She said, oh, no. Well, I couldn't work the farm without him. So she literally shakes him down for a little bit extra money. That could have gone to Newton having his own room and board paid for, but instead Newton had to work by cleaning the chamber pots, which means their poop and pee pots of their rooms of the wealthy kids. So that probably gave him a little bit of an attitude adjustment, made him a little bit of an angry person because he, was probably treated like crap by them. But anyways, he did go to Cambridge. I think he started at either 14 or 15. And he did well, but not so well that people remarked all these great things about him, because he really was in competition with the most elite, most educated, most wealthy people in the world, not just in Great Britain. But he was recognized as being good enough to get the Lucasian chair of mathematics, and that's probably the most esteemed academic position in the entire world. It's always held only by Brits, so in that sense, it's not that esteemed, just because it precludes you from hiring some really good people, like Sheldon Glashow might have been a good hire. I don't think Sheldon Glashow will be that good a hire, to be honest with you, but Salam would have been, or Steven Weinberg would have been, but they're, neither of those were Brits, so they wouldn't hire them. But to give you some idea, Newton was the Lucasian chair of mathematics. One of the other branches of physics beyond mechanics was electricity and magnetism, which was almost completely done by Maxwell. Maxwell was the Lucasian chair of mathematics. Quantum mechanics was related to relativity by a guy by the name of Dirac, and that guy, in fact, wrote his equation and was so confident that it was right that when people argued that it gave negative energies and therefore it couldn't be a physical equation, he said, no, my equation is right. That must mean that antimatter exists. So that guy Dirac, who literally just said, I'm right, I know I'm right, and I predict the existence of antimatter, and turned out to be right, he held it. Stephen Hawking held it till just before he died, and then after he died, Ed Witten, one of the co-founders of string theory, co-discoverers of string theory, now holds that position. So these are really brilliant positions, brilliant people that hold it. He held that position, and he pretty much spent his life trying to avoid interacting with people. We hear he's not that good of a teacher, but he was a really brilliant scientist and did a lot of great things. For instance, while he was at college, the plague occurred. Y'all wouldn't know anything about that kind of life, but anyways, they didn't know that much about the plague at the time, but they did realize that high density population areas were bad for it. So they sent all the kids home, and just like us good American kids, we get sent home. We go to Cabo, we go to Miami, or if you're really rich like me, you might go to Portsmouth, or maybe a hotel at Virginia Beach and stay a day. So anyways, Newton did the same thing. Newton just went back to his farm and, I don't know, invented calculus and created the Principia, basically the basis of the Principia, which was more or less writing physics from ground zero with almost no input. And it actually wasn't really completely with almost no input, but he's the one that saw it all so cohesively and put it all together in this book called the Principia. And at the time, physics was not a word they used. They just used the word natural philosophy, and his book was on natural philosophy. But he did amazing things. And when he says, I have stood on the shoulders of giants, when he says, I've seen further than others only because I stood on the shoulders of giants, that was somewhat correct. And it was sounding humble, but there's another meaning to it that I'll give you in a second. But it was correct in that Newton's first law of motion, the law of inertia, which is what Galileo had discovered, was the law of inertia. Newton had also came up with that, but just basically rewrote Galileo's discovery in a more coherent way, or I guess a more applicable way might be a better way to say it. So Galileo said that an object tends to move without changing unless something disturbs that motion, and it's as if it has some quantity called inertia, which we now know of as mass, And what that does is give you some sort of placeholder to put in your mind to not feel so bad about how you're smacking Aristotle in the face. Because Aristotle had taught us that there were two types of motion. There were natural motion and violent motion. And the natural motion occurred because of the 4 elements, or 5 if you count Mila Jovovich, which I'm sure I'm pronouncing her name properly. But anyways, the earth, wind, fire, and water, and then of course the quintessence, which is the heavens, which would have been Mila Jovovich because she was supposed to be the 5th element. But anyways, earth, wind, fire, and water have their natural places. So for instance, when you pick up a rock, you can only pick that up by violent motion because the rock has no desire to be up. But when you let it go, it will have natural motion where it's trying to get to its natural place, which is at the center of the earth, because yes, they did know the earth was a sphere at the time. So Aristotle, in fact, said that things travel naturally to their natural place, with earth below the water. The fire lifts up above the air because it's like the sun, so on, so forth. If you wanted things to make violent motion, you had to sustain them with a force. In other words, you had to keep them going by force. Otherwise, they're going to naturally come to a stop, which looks a lot like reality. But the reality is that that's not necessarily the case. It's just that there's forces that you didn't necessarily see. Like when you roll a ball down let's say a bowling ball down your street, it's going to come to a stop on its own. And it's going to do so because of friction and stuff of that sort, which isn't very obvious to the untrained eye. So that's what Aristotle sort of got wrong. And he also said that the object, say the rock, if you dropped it, it would fall and it would immediately travel at some speed that was related to its weight. So if you took a rock that was twice as heavy and dropped it, it would immediately travel twice as fast as that other rock, and so on and so forth. Galileo was like, okay, well, I know people have seen this and it looks really, really compelling, but in reality, objects tend to go on forever in exactly the same way, as if they have some reluctance to change. And that's what his inertia was. So Galileo had come up with that. And in fact, if you look in Leonardo da Vinci's notes, you will find one part where it literally says, it is obvious that if an eagle pushes down on the air with a force of 50 pounds, the air will push up on the eagle with a force of 50 pounds. So that's Newton's 3rd law, from good old Leonardo da Vinci. Now, the Newton's 2nd law really was what Newton did, among other things, of course, but that is one of the big things that he brought to it. So we'll talk about all those laws as well. Now, the part of that, if I have seen further than others, only because I stood on the shoulders of giants, was because he was addressing the Royal Society, and the president thereof was a guy by the name of Robert Hooke, which y'all might know from Hooke's Law, which we'll be talking about later. Is basically, we usually use it for spring, but it's true for everything. If you put a 2x4 under compression, like you put a big weight on top of it, the length of the 2x4 will shrink in proportion to that force. It compresses it, right? Or if you put it in tension, the length of that 2x4 will stretch in proportion to that force. But it's very small when you deal with that. If you deal with a spring, it works out really nicely and gets a very linear response. That's Hooke's law. But Hooke did a lot of other things too. He was a really brilliant scientist, but he seems to have had a little bit of a short person complex. I think he might have been 4'8". So he's kind of a small dude, but still, Newton's basically saying, if I have seen further than others, it's only because I stood on the shoulders of giants, not hobbits like you, Mr. Hooke. That was the underlying message. And of course, the reason he gave that message is Hooke was one of his enemies. He had many enemies, in fact. We found his journal. These scientists often kept private journals, and they kept scientific journals, and all of them they actually wrote in sort of codes, like they would make up their own code. And then if anybody just picked it up, it just looked like gibberish. But if they took the time to look around and find a primer, they could perhaps figure out what it said. And all my words are leaving me right now, so I can't think of words like what it means to decode something or something like that. There's a word for that, but translate basically, and that's not it either. But anyways, if you could translate that, then you could learn all sorts of private information.
Decrypt?
Or was that did you say decipher? Decrypt, yeah, decrypt was the one I was going for. Decipher was the one I was coming up with. Yeah, very good. Decrypt. If you did that with a scientific notebook, you could steal some of his scientific discoveries. If you did that with his personal notebook, you could find some of his private secrets, which could be embarrassing and all sorts of stuff. But they wrote them all very weirdly. Hooke had one, Galileo had them, Newton had them, Kepler had them, Da Vinci had them. when we finally discovered Newton's and then hatched it, we were really excited because Newton's this holier than thou character that bragged, you know, in his 80s that he had made it to that point in his life as a virgin because he was a true devout Christian who wrote over 500,000 words on the New Testament. He read the New Testament in the Greek that it was written in, and looked for messages from God via numerology, looking for the fountain of youth and ways to live forever, and looking for things like how to turn lead into gold and stuff like that. So he was really super devout. So people were like, "Oh, this is going to be really, really juicy. We got Newton's private notebook and we've deciphered it. Yay!" Well, you look at it and like the vast majority of the pages are like, "Forgive me, Lord, for today was the Lord's day and I worked," or something like that. I mean, really, really innocuous, minor things. But then all of a sudden you get to, you know, some really late page and it says, "Forgive me, Lord, for today I wish the death of 27 people." So you go from the extremely boring, not anything happening, to the extremely, holy crap, he wanted to set 27 people to die. So that's kind of crazy. And these people were very, very different characters than we're used to now. I mean, the closest thing we have to it in common written books is like Surely You're Joking, Mr. Feynman, where Richard Feynman got curious while he was an undergraduate in college and wanted to figure out whether ants, for instance, knew geometry, how they found their way, for instance, from the door of his apartment to his larder or something like that. And he would literally shuffle them around and see if they could find their way back. He found out, by the way, that ants mostly did not know geometry, but some ants in Brazil did. They seemed to understand, for instance, that the shortest path between 2 points is a straight line, little stuff like that. And he wasted, I say wasted, I wouldn't call it wasted. He spent a lot of time deciphering things like that because he was a naturally curious person. He did things like that and tried to figure out, you know, what it means to count to yourself and what are Mississippi's, one Mississippi, two Mississippi, that sort of thing. Very profound thought. And that's what these people, these Renaissance Enlightenment scientists were. They investigated everything. So one of the things Newton did was he pulled his eyelid out like this and jabbed a knitting needle in there and then pried it because he wanted to understand, having written, you know, 500,000 words on optics, he wanted to understand what the shape of the eyeball had to do with your vision and how that affected it. So you can look in his notebook or in his textbook on optics, which isn't really a textbook, but it's a book that could be used as a text, if you will.
Oh yeah.
And you will see it. Have you seen it?
Yeah, I've read all of this stuff. He also like stared at the sun for like 30 minutes and had to sit in a room for days. He also
He
apologized.
had to stare at the sun just because he wanted to see sunspots, and he hadn't figured out a way to do it without looking directly at it. And we get migraines where we have to stay inside for weeks or months in dark rooms. It was so bad. But yeah, he took this knitting needle in there, and you can see the drawing. It's like it's this big circle with lightning bolts
like a
shooting all
lobotomy.
out of it.
I've seen it.
Yeah, and I'm like, oh, that hurts so bad. But that's the kind of stuff he did. To give you another example, and this one's a little tawdry, but I like to share it because college students tend to pay attention when you say stuff that's a little tawdry, if you will. So they found Hooke's book, Robert Hooke's private notebook, and they were having some problem translating one little part, which they had translated to an actual word, which was helpful, but they hadn't figured out exactly what was going on. But for instance, one of his entries was woke up this morning 6:30 a.m., had beef, cheese, and port wine. Okay. Then it was followed by sweated 3 cc's. And you're like, sweated 3 cc's. Okay, cc's, 3 cc's, that's not enough for a person to sweat and keep track of. But what was it? Well, they finally figured out what it was. He was playing Uno, if you will. And at this time, it was a very important thing to consider. Is mass really conserved? So one way you might do that is consider, is it conserved in the case of life? So you would track down and weigh every ounce of food or liquid entering your body and every ounce of food or liquid exiting your body. And of course, that meant he had to keep track of that too if he was going to do anything like that. So yeah, that's one of the things they found in the notebook. So these people were very intense. Newton, for instance, also wanted to live forever, and he thought he could do so by drinking mercury. So as he became an adult, he drank mercury every day of his life. Really kind of an odd bug that way. But drinking mercury is might sound a lot worse than it is. We know, for instance, that they often tell pregnant women to limit the amount of seafood they intake, specifically because seafood often has mercury in it, mostly as a result of the petroleum products we put into the ocean, but partly because they get there naturally too. And they even, have to test fish from fishmongers to make sure there's not too much mercury in that. And so that makes you think mercury is very dangerous, and it is. And in fact, the Mad Hatters that you've heard about from Alice in Wonderland were actually groups of people that wore felt top hats, and they've discovered if you take mercury and rub it on felt, it actually makes it become chrome. And this is a time where you didn't have anything shiny like chrome necessarily, so it was really a cool effect. You could put on this hat, a top hat made of felt, and you could cover it all in mercury, and you wear it around all day, and you had this really cool hat. Well, the problem is mercury's got a really low vapor pressure, so you are constantly breathing in that mercury. You were probably ingesting it too, getting it on your hands and stuff like that. But the main thing was the problem that you were breathing it in, and it actually caused you to go insane. So that's where the Mad Hatter idea came from, because these people would literally go insane from the damage the mercury caused to their brain. Lead does a similar thing, by the way. Really screws you up in many ways. That was a big debate regarding leaded gasoline, which you can see a nice story on in one of the episodes of Cosmos, the new Cosmos with Neil deGrasse Tyson. But also, during that time period and thereafter, mercury was still used for a long time. In fact, we've now tracked more or less the entire trip of Lewis and Clark because of mercury. And what it is we know at the time period, basically the East Coast and maybe some sparse areas around the upper Northwest had quote unquote civilized modern society people there on occasion or living there. But everything else was basically the natives, which were not civilized and didn't know things. They hadn't really been through, let's say, the Stone Age or the Iron Age or anything like that. So they didn't know about mercury, for instance. And Lewis and Clark took mercury as an emetic with them. So, if you're drinking from a lot of questionable water sources, you're going to get dysentery, and you get dysentery back in that time, you die, right? It's a really horrible thing. So one of the emetics that they would take would be mercury. You'd ingest a certain amount of mercury, and that would settle your stomach and keep you mostly from dying, which is kind of nice. It's a mercury salt, I think, that they used. But we were able to locate sort of fossilized stool samples with mercury in it at various places, and from that have been able to put together the path that Lewis and Clark has taken. So mercury is bad for you, but it's probably maybe not quite as dangerous as we're protecting ourselves from. We could probably eat a little bit more mercury than the law allows in the US, and it might not be so bad. But like I said, I haven't done the science, so I'm not sure about that. So anyways, that's some of the weird stuff about Newton. Also late in his life, he was called to help the British community because there was a counterfeiter, and the counterfeiter was quite brilliant, and he was called to be the sort of the detective to look over and discover who the counterfeiter was and capture him. And ultimately he did win, but it was not an easy trip. So Newton had a lot of cool stuff he did. He did, like I said, invent the calculus. One of his enemies, as I told you before, was Robert Hooke. One of his enemies also was a guy by the name of Gottfried Leibniz. And both of them for more or less the same reasons. They both claimed to have discovered stuff that Newton actually discovered. One story goes like this: Edmund Halley and Hooke and some other people from the Royal Society were having dinner at a pub or something, and they were talking about just nature in general, and not like the ways that most of us do nowadays, unless you're a nerdy physicist. But they said, I wonder what kind of orbits can happen with a 1/r² force, meaning a force that if you double the distance away, you quadruple, or you cut the strength into a fourth. Or if you triple the distance away, you cut it by a factor of 9, or if you quadruple it, you cut it by a factor of 16. So I wonder what kind of orbits can come from such a force. And Robert Hooke said, "Oh, yes, I've worked this out." And he said, "Well, tell us about it. What is it?" He said, "Well, I can't really remember the details. Nothing special. I can show it to you." And they're like, "Okay, well, take us to your place." And so they go to his house, and he can't find his notes. He said, "No, it's no bother. I'll go ahead and do it again and bring it to you." Well, they waited months and months and months, and he never returned it back to them. And then on a whim, Edmund Halley said, well, let's go see that weird bird up at Cambridge, that the Lucasian professor of mathematics, Isaac Newton. And everybody's like, oh, he's kind of a nut job. You probably don't want to hang out with him. He said, well, he's nice enough when you're one-on-one. You just, he's a little irascible, but I'll go talk to him. So Edmund Halley, who actually became one of his good friends, talked to him. And he said, oh, yes, I've worked this out. It turns out that it's only conic sections. And he says, oh, really? Well, we're trying to settle a discussion. So could you provide these papers? He said, yeah. He starts looking for them. He said, well, I can't find them right now. I'll just redo them and send them to you. And he said, okay. And they're thinking they're on the same mission that they were with Robert Hooke. Well, the next day, the whole group gets them from Newton, and Hooke gets mad and says, oh, he stole my work. This is my work, not his work. And no, it almost certainly was not his work. Newton never went anywhere. He went to his house, he went to school, he went to church. That was it. In order for him to steal it, he has to go visit Robert Hooke or Robert Hooke's office or something. And he would never do that. He just didn't visit people. He was a loner. So most people don't believe that for 1 second. And that, of course, ticked off Isaac Newton, and Isaac Newton held that grudge forever. Hence the, today I wish the death of 27 people. He also did invent the calculus, and historians are almost completely convinced from that, as best I can tell, even though I'm not a historian, so I haven't talked to a lot of them. But we now have documentation that shows a common friend or a common acquaintance of Newton and Leibniz visiting Newton, and then Newton writing in his journal when that friend visited him that he had told him about his system of fluxions. And Newton, that's what he called calculus, is his system of fluxions. And he used all sorts of weird, ugly notation, because when you're inventing something, you don't necessarily know where you're going to end up. You don't know, for instance, that you're going to take a limit as some quantity goes to infinitely small of a slope or anything like that. So it doesn't sound reasonable for you to start off with dy over dx or delta y over delta x or anything like that. So he had dots and slashes and all sorts of weird crap he used. And that was really how he introduced his system of the calculus to people. Whereas this, explaining this to that common acquaintance, who then subsequently within a few days went and visited Leibniz, and then within a week or so, Leibniz publishes a calculus, beating Newton to the punch. Newton's enraged. He's certain this guy has stolen his information, and the evidence does suggest that that's probably the case, not only because of this mutual acquaintance, but when Leibniz delivered his material, he delivered it in the most beautiful form, like someone who really studied exactly what it was, looked back at it, and made all these wonderful symbols. The dy over the dx was Leibniz's discovery. The chain rule, how it looks like the top term cancels out with the bottom term to do the chain rule. How the integral was the area under the curve was a sum, so you make an elongated s. All that stuff was what Leibniz brought to the table, which sounds like someone who really knew what it was going to end up, or maybe started it way earlier and finished it way earlier than Newton. But then you're left with the question, if he published it that time, why did he publish it, quote unquote, so late? So yeah, I think most people would agree that Newton discovered it, and Leibniz might not have even knowingly stole it, because he could have just gotten been given the idea from the other guy and then ran with it, because he's a good enough mathematician to figure that out. If Newton gave this guy enough information that could give a good mathematician a hint, that might be all you need. So yeah, he had these enemies, and he didn't want them to die. At least initially, at some point in time, he was willing to say that he wanted them to die, but then he'd ask for the Lord's forgiveness to do that, for saying that. So anyway, so that's a little bit about Newton. A neat bird. It's always interesting to read about these guys. The other branches of physics, like I said, electricity and magnetism was largely done just by Maxwell. Of course, we had Faraday did essentially everything Maxwell had done, but just done in an experimental form and didn't know any math. He was a self-trained person, so he couldn't publish it in the appropriate ways. But he basically hinted at the existence of fields, which is ultimately what Maxwell did. Maxwell literally said, hey, I just looked in Faraday's notebooks and wrote all what he discovered in mathematical form, and it worked out great. And then later, a guy by the name of Heaviside made those equations, the stuff that Maxwell gave us, in a much more useful form. Instead of using quaternions and just language, he actually put it in a vector calculus form. And people like him and Gibbs and a couple other guys who were friends of his that of Heaviside that had met him. They made Maxwell famous, but it was after Maxwell had died, because Maxwell died at a young age of horrible stomach cancer. Without the respect of his peers, at least in the range of electricity and magnetism, because he also did other things like he's, another branch of physics is thermodynamics, and he did a great deal in that. Another branch of physics is astrophysics. He was the first person to really tell us what the rings of Saturn were and what they were made of, and proved it. So he did a lot of stuff too. Beyond that, so we've got mechanics, which is broken up into the dynamics and kinematics, and also fluid mechanics. Okay. Then we have, beyond that, we have thermodynamics, which I've talked about, Joule and Gibbs and Hamilton and various other groups of people worked in this area, Watts. Then we have electricity and magnetism, which is mostly Maxwell and Faraday and those people, but also Volta and Galvani and all those good things. And then beyond that, we get into the realm of basically modern physics, which is special relativity. Einstein publishes first. We start getting in general relativity, which Einstein played a part in, in quantum mechanics, which Einstein played a part in, but Bohr and Dirac and various other people, Heisenberg, for instance, all these people had other parts, Planck, to play in quantum mechanics. And then we also have nuclear physics, which is largely Enrico Fermi and other people later, Madame Curie, for instance, stuff like that. And we also have astrophysics and cosmology. So those are all the branches of physics, and we're now jumping into mechanics. Okay. So that's given you, I think, more than enough history for it, but we have a little bit of time, and it's nice to learn a little bit of history, because I never got any of that from my instructors. I just get it as you read along, and us old physicists tend to do that because our brains aren't cool enough to still do the highbrow mathematics stuff that we like to do, at least in some cases. So anyways, let's talk about Newton's laws of motion. So I've already given you some hints about Newton's first law, and Newton's first law is basically just that an object in motion tends to stay in that state of motion. That the word "that state of motion," those words are very important. So an object in motion tends to stay in that state of motion unless acted upon by a net external force. That's my wording of Newton's first law. An object in motion tends to stay in that state of motion unless acted upon by a net external force. And what do we mean by that state of motion? What we mean is if it's not moving, it's going to continue to not move. If it is moving, it's going to continue to move with the exact same speed and in the exact same direction. So I think you can probably guess where I'm going to go now. I can shorten that version to say an object in motion will maintain a constant velocity unless acted upon by a net external force, because velocity being starting with a V, vectors also start with V's. That's our mnemonic to remember that velocity is a vector quantity. And since it's a vector quantity, when you say it stays the same, that means its magnitude and direction stay the same. So an object in motion will maintain a constant velocity unless acted upon by a net external force, which, as I said, was, again, just another version of Galileo's law of inertia. Okay, so let me turn to my document cam and write some of this down. I'm going to give you on your notes for this class, I will give you some pages from another class. It'll say a lot of things that I normally don't take the time to write in a class. It's going to say them specifically because I took the time to write them, so I'll put it in there. So if you open up the notes for this particular class period and you see some pages you don't recognize, don't assume it's the wrong notes, it's the right ones. Okay, but first off, Newton's first law. What I'm going to say about that is just basically, and I probably need my glasses because I can't even see what I'm writing. That is actually Galileo's law of inertia. That's really all it is. And it's an object in motion tends to stay in that state of motion unless acted upon by a net external force. And one of the things you should learn to do as a logical thinker is learn logic a little bit. You know, if you can convert a statement into a if-then statement, like a law that you know happens to be true, if you can convert that into an if-then statement, then you can actually make it into the contrapositive and get a different but equivalent relationship. Because the contrapositive is always equivalent to the original if-then statement. However, the converse is another thing, and that's not necessarily the same as the contrapositive in the original one. And then another thing is the inverse, which again is not necessarily true just because the original if-then statement is true. But in the case of first law, they're all true. So it's really kind of nice. What you could say is if the net force, I'm going to write net force this way because see that sigma? What does that mean in mathematics? Anybody?
Sum of.
The sum of. So what I'm saying is sum up all the forces acting on a body. So this is the net external force is 0. Then its velocity is constant. So that's the original if-then statement. The variations are the contrapositive, the converse, and the inverse. Okay, so this is what helps me think of this. The converse, I think of Chuck Taylor's, the shoes Converse, and I think of Michael Jackson in the 80s wearing Converse doing that moonwalk thing. If you've ever seen the moonwalk, it's basically he's moving his feet and legs in the way you would to walk forward, but he's applying pressures in just the right areas so that he ends up walking backwards while looking like he's walking forward. That was the moonwalk. So converse tells me go backwards. Inverse tells me, since it's not going backwards, tells me to negate both things. And then the contrapositive, which I left off the cross on my T, the contrapositive tells you to do both the converse and the inverse. So the contrapositive is if, notice I've got to negate it and flip the order. So I'm going to say if the velocity is not constant, that's my negation by using the word not. If the velocity is not constant, then the summation of the forces does not equal 0. Okay, so that's the contrapositive. And remember, the contrapositive is always true if the original if-then statement is true. So that's something that's valuable just from a logic and reason standpoint. This is the kind of thing that Aristotle was awesome at. So I'm going to make this a little neater. So that's the contrapositive. So both of these, since the first one's true, this one has to be true as well. But in this case, these are also true, but they're not always the case. So I'll put little stars by them. The converse just says you're supposed to do it backwards, like I said, the moonwalk. So if the velocity is constant, then the net force, the summation forces equals 0. Okay, and then the inverse, you're just supposed to negate both of them but keep them in the same order. So you say if the summation of the forces is not equal to the 0 vector, then the velocity is not constant. Okay, so that's some logic that'll help you, I think, in the rest of your life in terms of arguing. Remember, if you can put make a law into an equivalent if-then statement, then the contrapositive will also be true. The converse and inverse, not necessarily. Okay, so watch out. I give you those mostly so you be careful and not make that mistake, but the contrapositive is doing both of those. Now, the second law, this is the part that I told you that that Newton really did do more or less on his own. And this is the version I'm going to give you. Later, we'll learn another version where we can learn some more stuff. But right now, we're going to give you this one. And it basically says, I'm going to use that same symbols, which your book doesn't use, by the way. I'm going to say the net external force. And notice I keep using this external force. I'll talk about that in a second. The net force acting on a body of mass m has an acceleration a given by F equals ma. Okay. So first off, this tells you that, notice is a vector equation, and when a vector equation exists, that means the left-hand side's magnitude and direction has to equal the right-hand side's magnitude and direction. So the magnitude of this must be equal to the magnitude of this. The direction of this must be equal to the direction of this. And since m cannot be negative, then we know ma and a are parallel. Since ma has to be the same direction as f, that means a must be parallel to f. So a is parallel to the net external force as well. And another conclusion is that a, the acceleration that an object of mass m gets, is equal to the net force and inversely proportional to the mass. Okay, when you compare an equation like this, on opposite sides of the equals, you have two numerators. A, for instance, is in the top of the fraction that doesn't exist because you can put 1 over it, under it. The A and the F are what we call thumbs up, thumbs up. What that means is if I double the total force, then I will double my acceleration. If I increase my total force by a factor of 1.79, the acceleration will increase by a factor of 1.79. But the A and the M are on opposite sides of the equals and opposite sides of the fraction bar, so they're thumbs up, thumbs down. And in this case, that means if I double the mass, the acceleration will go down by 2. If I triple the mass, the acceleration will go down by 3. Okay. A good way to think about this is if you want to hit a softball or a baseball really well, and by the way, because of this, you can see why we use softballs for old people like me in rec leagues and whatnot, because a softball is heavier than a baseball, and it's a little bit softer, so it doesn't come off the bat quite as fast. And it's a little bit bigger in radius, so it's got more air resistance, all of which points to the less acceleration off the bat. Okay. And obviously at one time they thought that women were incapable of doing the things men were, so that's why women ended up playing softball. And again, I'm saying they thought women were incapable of doing that. There are some things I'm sure that they're that differ us in races, but right now that's not really relevant. So if you want to hit a baseball, really what you're trying to do, if you want to hit like a home run, which is the, the sort of the holy grail of hitting, it's usually, it's the most valuable hit you can possibly do. There are some times where you just need a double or a single or a triple, but really the home run is the best you can do. And in order to hit a home run, you have to hit it really far. And to hit it really far, you have to take something that's coming at you and deliver it going away from you with as high a velocity as possible. That means the acceleration needs to be as high as possible. Well, this form of F equals ma doesn't show everything, but it does show us that one way to do that is to increase the force that you impart on the ball with the bat. Okay. So for instance, various companies make really nice bats that are designed to get even more pop off of the bat. So the ball can have even larger acceleration. So that's one thing, but that can only do a very small amount, but it can do some. The other thing is you're going to have to get stronger, and that means you're either going to have to hit the weights or you're going to have to hit the drugs. So that's why we've got a problem with steroids in sports, because sometimes it's just a little easier to get stronger by cheating as opposed to by lifting weights. So if you want to make your hitting better, you need to increase the force you can apply to the ball with the bat or with the racket in the case of tennis, which is one of my favorite sports, as well as softball. But that's the way you do it. Now, another thing you can actually do, but again, this version of Newton's second law don't show it, is you don't necessarily have to just increase the force. You could leave the force the same, but increase the time of contact between the ball and the bat. That's why your hitting coach will tell you hit through the ball, and that means very specific things that we'll talk about when we get to the momentum chapter. And they'll say swing level, and all those things sort of mean the same thing, but they don't mean what you think they mean in most cases, unless you're really good at hitting and know exactly what they mean. Generally speaking, they mean something very different than swinging the ball, the bat perfectly horizontal, or hitting through the ball doesn't necessarily mean just hit across the diameter of the ball. There's a different meaning to that as well, because the ball is actually moving while you're hitting it. So you want it to not go across the diameter at which you hit it, but in sort of some other direction. So we'll talk about that as well. But the other thing you can see is because the acceleration is inversely proportional to the mass, you can see why softballs leave slower. But you can also see a very good principle that I recommend to everyone is never, ever, ever pitch a golf ball to a baseball or softball batter. Okay, one, it could damage the bat, but two, it could kill you. Okay, the golf ball is made to do a lot different things than the baseball. It's made basically of a wad of rubber bands rolled up on top of each other, and then a hard plastic shell on top of that. So it actually can accumulate way more velocity from a given hard hit than a baseball or softball would do. And because of that, and because of the lower weight, the acceleration can be huge. So even if you're pitching from 90 feet away, even if you threw it from second base, you might be in danger of being killed by the baseball by a golf ball, if a baseball or softball hitter hit it, because it goes so fast. But that being said, if you're out in the open field, nobody's around, and you want to see something fly, smack a baseball with a crappy bat so you don't ruin it, and you'll see it's awesome. It goes forever. So that's Newton's second law. Let's now do Newton's third law. And Newton's second law is one of the two equations that probably a lot of people in the world know. The most famous one is E equals, anyone?
MC squared.
Yep, that's probably the most famous equation. This is the second most, but you don't see it anymore. I used to see it on ASICS commercials and basketball commercials and stuff like that. Occasionally you'll see it, but usually E equals MC squared comes up more. The third law is probably the most famous law that anybody can state. And I'll show you now. For every, anybody want to finish that? You can do it. You know it. You know you do.
For every action, there's an equal and opposite reaction.
Yeah, for every action, there's an equal and opposite reaction. That's a very good explanation of Newton's third law. I'm going to use a mathematical version that you guys have finished, at least one semester of calculus should be able to gravitate towards this quite easily. The force on object 1 as a result of object 2, that's what that symbol right there means. The force on object 1 as a result of object 2 is equal to the negative of the force on object 2 as a result of object 1. Okay, so there's the terminology you need to do. F12 is the force on 1 due to 2. Okay, now it's a vector equation, so that says their magnitudes have to be equal. But it's also a vector equation, so that means their directions have to be equal. So the force on 1 due to 2 has to point literally the opposite direction of F21. Because there's a negative here. Remember, when you multiply by -1, when you multiply a vector by -1, you just get the same vector but with the head on the opposite end. So this literally says that the force on object 2 as a result of 1 is the negative of the force on object 1 as a result of object 2. So if I kick a soccer ball perfectly horizontal with a force of, check out this unit now, 100 newtons, then the soccer ball hits my foot with a force of 100 newtons, but pushes backwards, so horizontal in the opposite way. That's it. That's the Newton's third law. And it seems like the most useless law, but I'm going to give you some ways to make sense of that in a second. So first off, let's consider something. Let's consider the world's simplest second law problem. So example 1. So we have a box that has applied to it a force F whose magnitude is equal to 100 newtons and is perfectly horizontal. Notice I wrote with no vector symbol on it because I was just writing the magnitude there. But we also have a force acting on it in the opposite direction. And that one has a magnitude of 5 newtons. And I use a script F because that's going to represent the friction. That's the F that we use for friction. So the left-hand side, if I want to solve this, I want to know what the acceleration is. And I know that the mass is equal to 9.5 kilograms. Okay. So I want to know what the acceleration is. So I take the left-hand side of Newton's second law. The left-hand side says the summation of the forces now is equal to blah, blah, blah. And in reality, what Newton's second law means is that the summation of forces in the x direction, that means all the individual x components of the force, is equal to the mass times the acceleration in the y and the x direction. If you add up all the y components of all the forces, that's equal to the mass times the y component of the acceleration, and the summation of all the z components of the forces is equal to mass times the z component of acceleration. So that's really what the vector equation means. You can put it in a coordinate system x, y, z. You can actually use other coordinate systems too, but you're going to have one of these equations for each of those coordinates. And these coordinates, since they're all one-dimensional, the x-axis is one dimension, the y-axis is one dimension, and the z-axis is also one dimension, then the direction is just indicated by a sign. Okay. So in this case, we're going to say the summation forces in the x direction, and I'm going to draw this as if this is my positive x direction, y would be there. Then I'm going to say 100 newtons plus negative 5 newtons gives me 95 newtons. So that's the left-hand side. So that's how we deal with it. We have to break our vector up into components in order to use Newton's second law. And therefore, the components can be positive and negative, but you're just adding them all up. That's why I took the time to write plus and then put a negative 5 newtons there. You're not subtracting any forces. You're always adding them, but some of the magnitudes can be negative. Now, the right-hand side of Newton's second law is m times a, which again was a vector thing. But in this case, we're just going to say m times a sub x, and that's going to be equal to 9.5 kilograms times a. Now, we know the units of acceleration are meters per second, right? And we know the unit of mass is the kilogram. So I think you can immediately see that 1 Newton is equal to 1 kilogram times, remember, a meter per second can also be written as meters per second squared. And we do write it when we're doing this, okay? It's just when we solve for acceleration, we want to write it in meters per second. They're exactly equivalent. You're not being wrong. It's just a little better to understand if you have it written that other way. So now I can set left-hand side equal to right-hand side. When I do that, I'll say 95 newtons is equal to 9.5 kilograms times a, which means a is equal to 95 newtons over 9.5 kilograms, which you can see if I divide a newton by a kilogram, I just lose that and I get meters per second squared. So this is going to be 10 meters per second every second. Easy peasy, right? So that's the key aspect, is you've got to decide on what your coordinates are. You know, if you're going to decide, maybe this is a symbol we often use, for instance, in statics, is you write x, y, and this, and just write plus. Okay, what that means is I'm assuming the x to the right is the positive direction, y up is the positive direction, and a counterclockwise rotation is the positive direction. We're not studying that rotation stuff yet, but this is a neat way of doing it. And you can just write that down and everybody will know, okay, he means to the right is positive, up is positive. He also means that z is positive out of the page, and that basically rotation in the counterclockwise direction is positive. That's actually equivalent to z being out of the page, by the way, but we'll get to that later. So that's a simple, probably one of the simplest examples of Newton's second law you can study. Further ones would be when I apply this force at an angle. And then I have some other issues, because when I apply it at an angle, say like this, then I have a component pushing down and a component pushing horizontal. only the horizontal is contributing to its motion this way. And in fact, the vertical is forcing it into the ground and maybe making the friction worse, which we'll discuss later. So now let's try a second example. And the second example is more of a conceptual one. Consider hitting a flying fly with your bare hand. Why does the fly rarely die? Okay, so that's a neat little question. Why does the fly rarely die when you hit it in the air? There's two answers, and one sounds really simple and straightforward, but when you start to think about it, you're like, ugh, I don't feel good about that. I feel like I feel like I did a politician thing with that. Okay, but it is accurate. Okay, the other one sounds messy and convoluted, but it's accurate, and you don't feel like a schmarmy, slimy, unctuous politician when you're done, because you really explain the details of it. So I'm going to do both of them. So one solution is, according to, whoa, hate it when I do that. I think of the next word down the line and I end up writing the wrong letter. According to Newton's third law, your hand can only apply a force as large as the fly can apply to your hand. Okay, so and that's true. You know, Newton's third law says the magnitude of the force my hand applies to the fly is equal to the magnitude of the force the fly applies to my hand. So according to Newton's third law, my hand can only apply a force as large as the force as the fly can apply to your hand. Flies are small. So they cannot apply much force.
Sounds good.
Right? That sounds it sounds right, but it's sort of like it just feels like I didn't quite answer the whole question, right? At least not enough to kill itself.
Well, it's also because there's nothing to.
You most likely
force
will stun it
acting
though.
on it.
Yeah, so you seem to be getting it a little bit, right? It makes some sense. It's easy to say. It's nice. I want to give it a little bit more legs though, so you can really understand. And like I said, this is the correct answer, and it makes sense, right? It's just a little, like I said, it didn't fill in the gaps enough for me. So I'm going to do solution 2. If you are a professional baseball player or pitcher, let's say, you may
be able to swing your hand at 100 miles per hour.
Right. That's a pretty good pitch for a professional pitcher. Pitch 100 miles per hour. A lot of them don't even do near that. A lot of them use the motion of their pitch more so than the speed of their pitch. You know, fast curveball pitchers and knuckleball pitchers, stuff of that sort. So you immediately want to think, okay, well, let's imagine this scenario where I'm really, really awesome. My hand can move at 100 miles per hour. When I do that, then I can say, oh, well, what really happens when I hit a fly? Well, when you hit a fly, what happens is your hand comes flying by at maybe a maximum of 100 miles per hour, and the fly hits it and compresses its body in your hand just a little bit until finally the fly is going the exact same speed as your hand, right? Assuming the fly was so light that it didn't slow your hand down, which is, you know, fairly realistic. So this means the fly will be accelerated to 100 mph, which, by the way, is 44.7 meters per second. Okay. So the fly is going to be accelerated to 100 miles per hour. Let's assume, just as a rough ballpark, I doubt it's 100th of a second, and I certainly doubt it's a whole second. I suspect a good estimate of how long the hand is going to be in contact with the fly to speed it up is going to be about 1/10 of a second. So assume delta t equals 0.10 second. Then A is equal to V final minus V initial over delta t, gives us 44.7 meters per second minus 0 over 0.10 seconds, which you see is an acceleration of 447 meters per second per second. That's more than 45 G's. Okay. So that sounds bad, and that might be able to kill it. But if you're thinking in terms of what force you're applying to the fly, you then have to use Newton's second law. Now, the hand is obviously the biggest force applied to this fly, and it's greatly bigger than anything else, like the gravity or whatever. So the summation of the forces on the fly is essentially equal to the force by your hand. Okay. Therefore, the force by your hand is equal to the mass of the fly times the acceleration. Well, if you look up a fruit fly, you will find that its mass is at most around 0.3, or excuse me, 0.003 milligrams, not grams, milligrams. Okay. So I have to basically convert that to grams by realizing that 1 milligram, or excuse me, 1,000 milligrams is equal to 1 gram, and 1,000 grams is equal to 1 kilogram, and then multiply that by 447 meters per second per second. And when I do that, I get basically a really, really small force. In fact, the force is 0.001 newtons. So you see, because the fly's mass is so little, it took nothing for me to bring it up to, 447 meters, or excuse me, 44.7 meters per second. So that's another reason for it. And I think that one's a little more fulfilling just because you can sort of see, oh, okay, well, yeah, that acceleration for the fly, that probably wasn't comfortable for him. He might even have some brain damage as a result of that. You'd be hard to do a standardized test on him. But the main thing is, yeah, he's not going to die because that's a teeny force. For instance, even if you compare it to its mass, well, if you compare it to its mass, it would be pretty big, but it's still a fairly small force. So that's a way of looking at it. Now we've got about 6 or 7 more minutes. So I'm going to show you yet another example of applying Newton's second law. We did some time ago, we talked about the Tesla Model S Plaid. And in fact, we discovered that the Tesla Model F Plaid could actually reach 0 to 60 in 1.98 seconds. So let's consider if we assume that acceleration is a constant, which we've done over and over again, which isn't necessarily true, but probably is a little bit more true than the case for the Mustang or something like that. Let's consider that now, what's the average force required to do that? So this is example 3. So the Tesla Model S Plaid. Again, that is the way you spell plaid, but I'm not sure he meant us to pronounce it plaid. But either way, its mass is about 4,776 pounds, and which technically is really its weight, not its mass. Okay. But you can convert that to newtons by doing 4,776 pounds times a conversion factor, and it turns out that 1 pound is equal to 4.448. So that's nice. We've now gotten a little bit of information about the Newton. Remember, I told you the Newton is the unit of force we use in the SI. Well, it turns out basically a Newton is about a little bit smaller than 1/4 of a pound, because if it was exactly 4, it'd be 1/4 of a pound. So you could imagine sort of taking a 1/4 pounder burger that's frozen, cooking it, which melts away all the water and removes some of the grease, and then dry it off really well, and then weigh it, and that's about 1 Newton. So it's about the mass of a fully cooked and strained and drained and dried 1/4 pounder. Okay, just the burger, not any of the toppings. So that's roughly what a Newton is. It's pretty small. When we do that, we find out that this is 21,244 newtons. So that's the weight of the Tesla, is 21,244 newtons. Now, I will tell you this, and we'll discuss it later, but weight is actually defined to be mass times gravitational acceleration. Now, that's what it is for a given value of G. So for instance, if I go to the top of Mount Everest, G changes, and in fact, my weight will be a little bit less. If I go down to the bottom of the Marianas Trench, then G changes again, and my mass will be, my weight will be a little bit larger, okay? But we're going to take sea level to be the norm, in which case we'll say 21,244 newtons. And actually, I've got an extra sig fig there. I started with 4, so this one's extra. That's equal to the mass in kilograms times 9.80 meters per second per second. That's going to cut me down to 3 sig figs. So all I have to do is divide that 21,244 by 9.8. And that gives me 2,168 kilograms. Now, that's 1 extra sig fig as well. So if I want to find now this is the total force, but in reality, the total force would be the force that the car is supplying minus the force of air resistance, minus the force of friction, all that stuff. I'm just going to pretend like this is just the force of the engine, and we'll actually get a conservative estimate. In other words, the engine is going to be more powerful on average and have more force on average than what we determine. So I'm going to say the total force is about equal to the force
that the Tesla can deliver. Okay, that will be equal to 2,168 kilograms times, if you guys remember, 60 miles per hour was 26.8 meters per second. So that'd be 26.8 meters per second minus 0 meters per second over 1.98 seconds. And when you compute that acceleration and everything, what you'll find is that's 29,356 newtons, which we really should round to 29,400, or specifically, so there's no ambiguity whether these two are significant. So you could write it as 2.94 times 10 to the 4. That's pretty big. In fact, you could convert that back to pounds if you wanted, and you'd find this a pretty significant number. You'd actually have to divide it by 4. So it'd be smaller than maybe 7,000 pounds. It's probably about 3 tons. So that's another example of how to apply Newton's second law in a very simple case. Now, just as a idea of letting you know how valuable Newton's third law is, if you really wanted to figure out what force the Tesla was given, you'd be at a bit of a problem, because we know right now, if we can assume this is a conservative estimate, we have some idea about what that force is. That's the force that forces a Tesla along. But if we try to figure that out just by knowing the schematics about the engine and its capacities and stuff like that, we'd run into some difficulties. So you might be able to determine in a lab or using a dynamometer or something like that. You can tell, for instance, the force that the engine applies to the transmission, or that the transmission applies to the drive shaft, or that the drive shaft applies to the differential, or that the differential applies to the axle, or that the axle applies to the rim, and then the friction that holds the tire to the rim applies through the tire. But then what you've done is you found the force, if you actually know, say, for instance, that torque that's applied to the wheel, then you can multiply that torque times the radius of the tire, from the center of the rim to the outer edge of the bottom edge of the tire. If you multiply that distance by that torque, divide that torque by that distance, not the other way around. If you divide that torque by that distance, you'll have the force that the tire actually applies to the road. But guess what? That's the force the tire applies to the road. That's not what F equals ma is about. If you're wanting to figure out what the acceleration of a car is, you need the force that's actually acting on the car, right? Or the tires. Because those other forces, me applying my foot to the gas pedal, well, my mass is included in that M for the car. So me and the car are part of the car. That's one of those internal forces that I was warning you about. You can only, you can't lift yourself up by your bootstraps, despite what Andrew Jackson said. You can only take the forces that are applied to the mass M by other objects. So the force I apply to the gas pedal, irrelevant. The force the transmission applies to the drive shaft, irrelevant. The force the engine applies to the transmission, irrelevant. All that stuff's irrelevant. Even the force that the tire applies to the ground is irrelevant unless you use Newton's third law of motion. Okay. Once you use Newton's third law of motion, you say, okay, wait a second. If the force that the tire applies to the road is 29,000 newtons backwards, then according to Newton's third law, the road is going to apply a force of 29,000 newtons forward on the tire. And that is exactly the force that you're supposed to put on the left-hand side of Newton's second law. Of course, you still need to include the air resistance and friction and stuff like that. But that's how you see that clearly Newton's third law of motion seems like the least valuable, but in fact, you can't solve a lot of problems without knowing it. You can't even talk about yourself and your ability to walk on a surface, because you can pretty much figure out what force you can apply to a surface. But without Newton's third law, you can't figure out what force the surface applies to you. So that's it. That's our intro to chapter 4. You folks are free to go. I'm going to wait here again for the last person to finish up, but you all are free to go and have a good time. And I will see you next time, and we'll do some more on chapter 4.
Thank you.
You're welcome.
I do have a question on the MyLab and Mastering.
Go for it,
I
Sam.
do too.
The
Okay.
chapter 4 homework for MyLab and Mastering didn't change due dates. It's still
Yeah.
due
I've
yesterday.
got to change it today.
Okay, cool.
Yeah.
Okay,
I was-
are you gonna change the other chapter, like chapter 6? Because there's another
Yeah,
part,
everything will be
chapter
changed.
3.
Remember, the dates are irrelevant for a given chapter until I start that chapter. So now that I've started chapter 4, I've got to go back and fix that. And in fact, I got to do it for all 3 classes today. So all 3 of my 241 classes will have a different date today. And I'm probably going to make the chapter 4 homework due Wednesday, but the chapter 4 concepts will be due probably Sunday.
You mean this weekend?
Yes.
Okay, and this chat and hold on, sorry, let me think. The chapter 6 will be changed too, because that says it's due this. It's gonna be due next week.
Yeah,
and
it's
I
not
wanted
going to,
to
it's
get-
not going to count against you or anything like that. I'm going to change the date for chapter 5. That'll probably be due a week from the due dates for chapter 4, and then 6 will probably be due a week from that.
That sounds cool. Thank you.
Okay.
Chapter 3 is still due. Well, it'd be tomorrow.
I think
And
you
then
got
the
till
next
tomorrow
part.
to do it. Yeah.
All right, cool.
And also, what about the test 2?
Test 2, I put up the practice test last week.
I saw
I think
that.
I'm going to put up the test 2. I'll definitely put it up by Friday, and you'll probably have until Monday to do it, maybe Monday or Wednesday. I haven't decided on that yet, but I'll
Thank you.
definitely put it up by Friday.
Okay,
Anyone
cool.
else?
The
Boy.
practice test is still locked.
Yeah, I keep the practice test up. Oh, are you saying it's not up?
It's locked.
Oh, okay, I will go in and change that. That's a screw up on my behalf.
I got a lab book. Like I rented, I ordered one online,
Okay,
and it still hasn't gotten here yet. So do I just hold off?
I'll give you the lab tomorrow, and when you do get it in, make sure you confirm that you show me it. Okay.
All right, sounds good. Because I haven't started the second lab yet. Because I didn't really have anything to do with it because I didn't have the book at all.
Okay, remember, I actually been giving that to everybody, so you still want to go ahead and do it. There's no reason for you to be late just because you don't have your manual. I actually gave.
Oh, I thought you
everybody the
gave
lab.
everybody the first one. I didn't know you gave.
No, I
people
gave them the second one too. It's on there still.
Oh, all right. Thank you. I'll check that out.
No problem.
I have a question regarding lab attendance for the second one,
Yes.
because according to the grade, I have a 0 on it,
Yeah, I
despite
do
the fact
too.
I was
Total
poorly
0
present.
or like a 50.
It was like
zero
a
total.
0.
Okay, I'll check that, and I might have made a mistake in your case. Sometimes I'll type it in a line and it'll be the wrong line. But what I was going by for lab 2 is I pulled your attendance according to the report that Zoom gives me, and basically people that spent less than, I think, 28 minutes or 29 minutes in the lab cumulatively, they didn't get credit for being there. And then if you didn't turn it in on time, you didn't get the other 50 either. So if you've turned it in on time, you should at least have 50. If you stayed there for 29 minutes, you should at least have 50. And if you did both of those things, you should have 100, but I'll check it. Gerald Harris is your name, right?
It
Right.
grade-
Anybody else have that
yeah,
problem?
I also got a 0, sir.
That's Colby.
It graded it. Gave me a 0 before I even turned in the lab report. I turned that in yesterday, I believe.
Okay,
Or
I'll
a
check
couple
that.
days
And it's
ago.
Colby Daniel and Gerald Harris. Gotcha.
And when we were in there probably till 12. I mean, not. I'm trying to think the time. It was like because it closes at 10:50, right? So we were in there till 10:20. We finished like 30 minutes early because we had pretty much gone over everything in our lab. I messaged you on the Zoom.
Yeah,
thing that
like I said, I'll
we had
double check that.
finished.
I'll tell you something else that happened was I had inadvertently mistook lab 1 and lab 2, I think. So at one point, I literally traded the attendance grades for lab 1 and lab 2. So I would not be surprised to find some errors in there. So I'll go check them for Colby and Gerald.
Yeah, because we were lab partners. Thank you.
Yeah.
No problem.
All right.
Thanks, guys.
I have a question concerning lab 2, just
for it,
for like
David.
the graphs, like in the actual document, do we have to recreate them, or can we just like take a screenshot of the ones like on Canvas and just copy and paste that over?
Unless I explicitly tell you to draw something, then you can just take a screenshot. That's fine.
Okay.
Sometimes it's even better to do both. That way, you know, I can sometimes give you extra credit.
Okay, well, sounds good. Thank you.
Okay. And you're never printing it, so it's not going to waste paper or anything.
Yeah, correct.
Mark, Manny, do you have anything? All right, I'm out of here, folks. See ya.